Thevenin's theorem and its applications. We will discuss in this lecture about Thevenin theorem and how Thevenin theorem is used in different circuit theory and network analysis problems. In fact, there are many network theorems. Thevenin theorem is one of the most important theorem in any circuit theory concept and network analysis. Thevenin theorem is very popularly used in many applications, right from circuit theory to transmission line to analog electronics, so on and so forth. And therefore, we will discuss in this lecture about the statement of Thevenin's theorem, the importance of Thevenin theorem, and its applications. The outline of lecture is we'll discuss learning objectives, Thevenin's theorem statement, few examples and applications. Let us begin with lecture objectives. One of the objectives is to understand Thevenin theorem and simplify some electrical networks into simple equivalent circuits using the theorem. That is one of the objectives of this lecture. The second is to study an application of theorem. If we see an example of network, which is network number 1, this is a network where we can see that there are two sources, energy sources. One is voltage source and there is a current source, and there are many other elements. These resistances are there. There is a second example where there is a transistor NPN transistor amplifier, where there is a divider circuit consisting of R1 and R2. These are simple circuits where right from simple circuit to transistorized circuit, the Thevenin theorem is greatly used to simplify and obtain the equivalent circuit. If we go to the Thevenin's theorem statement and if we read it, the statement is very simple. But the important line is linear and bilateral network. Any linear and bilateral network. Any linear and bilateral network can be converted or can be replaced by an equivalent circuit which consists of a voltage source and in series with a resistance. The voltage source we call as a Thevenin voltage and the resistance is called as Thevenin resistance. Thevenin voltage and Thevenin resistance. The Thevenin voltage is also known as open circuit voltage. We will discuss because the Thevenin voltage is always calculated across the load where we are interested to determine Thevenin, and our Thevenin is the input or equivalent resistance at the terminals wherever we are determining the Thevenin equivalent circuit. If we see the circuit here is a linear circuit and there is a load, what we do in getting Thevenin equivalent circuit, we replace the entire circuit by a single voltage source in series with resistance, and then we can connect the load wherever we want the Thevenin equivalent circuit. How do we determine? Now, right from we take any circuit and we are interested to convert, we are interested to replace by a simple equivalent circuit. So how do we convert equivalent circuit? And if we are interested to convert equivalent circuit, we are required to calculate Thevenin resistance and the Thevenin voltage. Let us begin with determination of Thevenin resistance. Actually, if we see the Thevenin resistance, it is also known as the resistance seen by the load. What is the resistance seen by the load? So we are interested to calculate the resistance, which we are also calling as the internal resistance of a network. So what do we do? Since it is a resistance seen by the load, we remove the load and all the independent sources are turned off, which means that if there are voltage sources, they are replaced by a short circuit, and if there are current sources, they are replaced by open circuit. Let us take one example. There is a simple circuit. In one we can see which consists of R1, R2, R3 and load resistance RL. There is a source. And if we are interested to determine Thevenin resistance, what we do? Immediately, if this is an independent source, See, we can see in circuit number 2 it is replaced by a short circuit. What about here? We are interested to determine Thevenin resistance, so we remove the load, and now looking into these terminals A and B, we can see that this R1 and R2 becomes parallel, and this parallel combination is in series with R3. One can see here in circuit number 3. And finally, the Thevenin resistance is nothing but R3 in series with parallel combination of R1 and R2. How do we determine open circuit voltage? Next, that is Thevenin voltage. We determine open circuit voltage, that is Thevenin voltage, putting the load under open circuit condition, because we don't want that if there is a supply, if there is a voltage, that effect will be there in the network. We want that what exactly is the voltage due to the current and voltage sources which are present here across between these two terminals, across this load. And therefore what we do that we don't allow any current to enter, so that the voltage is not affected between the two terminals, and therefore we calculate open circuit voltage. So we can see in the same example that the load becomes open circuit, and if this is open circuit, there will not be any current across R3, and therefore whatever is the voltage across R2, that will be Thevenin voltage. So across R2 means there is a voltage divider, R2 divided by R2 plus R1 into Vs. We can see here is the Thevenin voltage. What will be Thevenin resistance if it is removed? And this is nothing but we have already determined R1 and R2 are connected in parallel, and they are finally connected in series with R3. And this we can see the Thevenin resistance and Thevenin voltage. Then finally load can be connected, and this actually becomes Thevenin equivalent circuit of the given circuit. Let us discuss some examples. This is an example where we can see there is a 10 volt DC battery, then 2 ohm, 2 ohm, 2 resistance, and there is 1 ohm. If we are interested to determine the Thevenin equivalent circuit between A and B, that is across AB, we are interested to determine Thevenin voltage. It's very simple, that there will not be any drop across 1, so this 10 volt will be transferred across 2 divided by 2 plus 2 into 10, this becomes 5 volt. What about Thevenin resistance? This will be replaced by 0 volt, that is short circuit, and 2 and 2 will become parallel, we can see here in circuit number 2, and then this will become in series with 1. So what is the Thevenin resistance? That is nothing but 2 ohm. And final Thevenin equivalent circuit will be 5 volt of Thevenin voltage in series with 2 ohm resistance. That is Thevenin resistance. There is another example. We can see that there is a 30 volt and AB is the load, and we are interested here. Very simply, there is no voltage across 4 ohm. Similarly, so we will transfer our voltage across 6 divided by 12 plus 6 into 30, that is 10 volt. How will we determine the Thevenin resistance? 12 comes here, see that in parallel with 6 and in series with 4, that comes as 8 ohm, because 30 volt here is an independent source. There are variations when dependent sources are there in the circuit. Right now we are discussing about presence of independent source only. There is another example we can see here. There are two sources. There is a current source and there is a voltage source, and it has been asked to determine the Thevenin equivalent circuit across AB. And if you are interested, let us try to find out the open circuit voltage, that is between A and B. How will we determine? There are different ways in which we can determine. There is no current at all, so we can see that this 1.5 ampere will go here, and this 1.5 ampere will enter, we can see, through 20 ohm, but whatever current is coming from the source minus 1.5 will come here. So this 1.5 and 1.5 will cancel. It means that this 1.5 will be flowing like this, and here this 1.5 and minus 1.5 will cancel. It means whatever current is flowing in this loop is the loop, that's all, and that is flowing through the 20 ohm. So how will we determine the Thevenin voltage, that is between A and B? Of course, this is the voltage between, that is across 10 ohm plus across 20 ohm. What is the voltage across 10 ohm? 10 into 1.5, since it is entering, so it is 15 volt, we can see here. What about 20 volt? How can we determine? We can put a voltage divider, 20 divided by 20 plus 5 into 20, and if we add these two, it becomes 31 volt. So 31 volt is the Thevenin volt, that is open circuit voltage. How will we determine Thevenin resistance now? There are two sources. This becomes short circuit and this becomes open circuit. So 5 and 2 becomes parallel and they are finally connected in series with 10. And this becomes 14 ohm. And finally, the equivalent circuit can be drawn as 31 volt in series with 14 ohm. And the load is now connected back 17 ohm. And if someone asks that what is the current through this load, what is voltage across the load, we can easily determine. If you are interested to determine current, 31 divided by 14 plus 17, 1 ampere current is flowing in the circuit. And what is voltage across AB? That is 17 volt. So this is another example. Let us see one more example where we are asked to determine voltage drop across RL. Where is RL? This is a bridge where RL is there. RL is there. There is load 2 ohm is connected between A and B. And we are interested to determine Thevenin voltage and Thevenin resistance. Let us determine Thevenin voltage. That is, we are interested VAB. That is open circuit voltage. Once we say open circuit voltage, no current is entering from A and B to the network. You can see here. So this VAB will be nothing but the voltage between voltage difference between A and B. Very easily we can do. Once it becomes open circuit, this 3 and 6 becomes series. Similarly, 6 and 4 becomes in series. And this 3 plus 6 is 9 and this 6 plus 4 is 10. That is 6 and 4 and 3 plus 6. So we can determine the whole amount of current here. Or else what we can do, that this 30 volt is across this as well as across this, because they are connected in parallel and this is open circuit. And how this 30 volt will be divided between these 3 ohm and between 6 ohm? Voltage divider. If you are interested across 6 ohm, that is 6 divided by 6 plus 3, that is 6 divided by 9 into 30, which comes as 20 volt. Similarly, we can calculate voltage across 4 ohm. This is 4 divided by 4 plus 6 into 30, that becomes 12 volt. Why we are interested here and here? Because this VAB is nothing but voltage difference between these and these, which is 20 minus 12, and therefore it is 8 volt. That is VAB is equal to 8 volt. And now we are interested to determine Thevenin resistance. What is the value of Thevenin resistance here? The Thevenin resistance will be, we can see here, and since this voltage is minus 30 volt, well, one more thing is important. Therefore, this VAB will also be minus 8 volt. We are assuming that this is 10 volt is actually minus 10 volt and this is minus 20 volt, because this supply itself is minus 30 volt, which is connected. So the Thevenin voltage VAB is minus 8 volt. Now how will we calculate Thevenin resistance? Very simply, this becomes load where we have to determine Thevenin resistance. This becomes short circuit, means this D and C are connected together. See here, D and C. And if we do so, very easily we can understand this 3 becomes in parallel with 6, because we can fold this like this and holding this wire. So this 3 and 6 can 3 and 6 are connected in parallel, and 6 and 4 are connected in parallel, and they are connected in series. We can see here 3 and 6 and 4 and 6, and they are connected in series. So this 3 and 6 gives 2 ohm and 4 and 6 gives 2.4, and they are connected in series. So it is 4.4 ohm. And the final Thevenin equivalent circuit is 8 volt connected in series with 4.4 ohm. And if we are interested how much current is flowing through 2 ohm, we can calculate 8 divided by 4.4 plus 2, that is 1.25 ampere. This is how we can solve all simple and simple to complex circuits when there are independent sources present. There is another example where there is a dependent source and there is independent source also. See, in the circuit, 86 volt is the independent source and there is a 6S which is dependent. How will we determine, that is Thevenin voltage and Thevenin current, Thevenin resistance? So we can see here the circuit number 2, where what we have done, we have removed the load. That's all. If we go to 3, we are interested to determine the Thevenin resistance. Now we can see in determination of Thevenin resistance, this 86 volt which is independent is off now, is replaced by a short circuit, but still we cannot determine because there is a 6 is, and this is this current, is a dependent source. What is other way? We can connect a battery here. There are many different ways. We can determine Norton current and then open circuit voltage, or else we can connect a battery. So we can see, we can do like this. That is, we are just connecting a current source here. Voltage across is V and current entering is 1 ampere. We are just assuming any current we can enter, any current can be considered. Even we can assume that there is a V and current entering is I, and we can calculate V by I as a Thevenin resistance. But what we are assuming here, for the sake of simplification, 1 ampere current is entering and there is a voltage between these two terminal is V. So can we write one simple KVL, and that is, how can we write this KVL? Here is and we are interested to determine this is. So this 1 ampere enters, what we can write, there is a KVL here and there is another KVL we can write here, that is 50 is plus 30 into is plus 1 plus 6 is equal to 0. We can see here, and the is comes as this. And what is second one? Second KVL which can be written from this circuit diagram, easily we can write, because load is removed, that is 86 equal to 50 is plus 30 into is, because this is open circuit, we are interested in determining Thevenin voltage, plus 6 is. So this is how we can calculate because this is VAB. What is VAB? Is 30 into is plus 6 is. So 30 is plus 6 is comes as 36 volt. So this 36 volt is the open circuit voltage, which can be calculated from circuit number 2 itself. Now you are interested in determining Thevenin resistance. What is is here? Minus 5 divided by 43. Now we can see here that we can write some other KVL. We can write KVL for in terms of V now. In terms of V, if we write V is equal to this 40I plus 30 into is plus 1. Now we are assuming 1 ampere current entering from this battery plus 6 is, and another KVL is 50 is plus 30 is plus 1 plus 6 is equal to 0. And if we solve these two, and since we already know the value of is in the previous circuit, so if you substitute is, you get V is equal to 57.4. What is this V? What is resistance? What do we want here? Resistance seen by this load, and that is nothing but V divided by I, V divided by 1. So V itself 57.4 becomes Thevenin resistance. Finally, substituting these values, this becomes Thevenin equivalent circuit, and we finally get voltage across 100. If we are interested, we'll get 22.9 volt. After discussing about Thevenin theorem and statement, its significance and few examples, let us try to understand where do we use Thevenin's theorem. It's mainly used to determine change in load voltage, because we can see that in all the calculations of Thevenin, either we are interested to determine current through load, voltage across the load, or if you are calculating Thevenin voltage or Thevenin resistance, load is something which is very important, playing a significant role. So if there is change in load voltage, how does it affect the network? To predict range of load voltage variation due to change in load resistance. If load resistance varies, what will be change in load voltage? Second is to obtain Norton equivalent circuit, since it's a dual of Thevenin theorem. There is a duality between Norton theorem and Thevenin theorem. And third, which is the most important property, I can tell you, most important application of Thevenin theorem is maximum power transfer theorem. So let us try to discuss maximum power transfer theorem. Maximum power transfer theorem, the statement says like the maximum power from any network can be transferred to load. Any network can be transferred to load when the load resistance becomes the internal resistance of the network. Now in this example, that is in this theorem, we have replaced the entire network by a Thevenin equivalent circuit. We can do it because Thevenin theorem we are using. So what is the internal resistance of the network? Is nothing but the Thevenin resistance. So what is maximum power transfer theorem? It says that when this load resistance becomes Thevenin resistance, which is the internal resistance of the whole network from where we got this equivalent circuit, when they are equal, the maximum power will be transferred from the network to the load. What maximum power and whether RTH is equal to RL comes as the true condition for maximum power transfer. Let us understand. What is power across RL? We can determine I in this loop, that is VTH divided by RTH plus RL, and we can calculate power across RL, I square into RL, like this. Whenever we understand that there is a maximum power or there is something which is maximum, we know mathematically that its first derivative is equal to 0 because we are discussing it with respect to RL. So if you differentiate with respect to RL, it becomes 0. And if you differentiate this dP by dRL, and which we equal it to 0, we'll get RL equal to RTH. We get RL plus RTH equal to RTH. So it gives you RL plus RTH. What does it mean? This is the condition whenever the load resistance becomes source resistance, that is internal resistance, not source of the network, maximum power will be transferred. How to calculate maximum power? In the expression of this power, we can substitute the value. So what maximum power is coming? VTH square divided by 4 RTH. So we can understand any maximum power transfer theorem problem without using network theorem, that is Thevenin theorem. It's very difficult to determine. And if Thevenin theorem is there, we can easily calculate what maximum power is being transferred from any network to the load. I can tell you this concept is used in electrical circuit. This concept is used in semiconductor. In rectifier, we might have studied that the source resistance that is Thevenin resistance, internal resistance of the network becomes the load resistance, that the maximum power is transferred in the rectifier circuit. So that is in the case of rectifier circuit, that load resistance becomes RF, which is the internal resistance of the diode, which is there as the most important element in the half-wave rectifier. But anyway, what do we want to say is maximum power transfer can take place when the internal resistance of any network, this linear and bilateral network, it gets transferred when the internal resistance becomes load resistance. So this is what we wanted to discuss about Thevenin's theorem. There are a few problems which are already there in my channel, but I wanted that the intricacies, that is how can we discuss Thevenin theorem in simple words. So we talked about Thevenin theorem and statement, a few examples, and the different uses, that is applications of Thevenin theorem. You can kindly visit for more such videos in my YouTube channel. There is a link for that channel. I believe that this Thevenin theorem concept will help the students and learners to simplify so many electrical circuits, right from basic electronics, analog electronics, to circuit theory, to transmission line, to get equivalent circuit, and to calculate the unknown current and unknown voltage across load resistance or load impedance. Thank you.